This is a problem about energy and intensity and power. So let's go ahead and take a look at what it's about. Okay, and for starters, we'll note this. The question is asking about the power produced by a solar panel. Okay, and the solar panel produces 1 kilowatt of power when the panel is turned towards the sun. Now let's think about this. If I have a solar panel and sunlight is falling on it, it's going to produce energy. And the energy it's going to produce is given by this. The electric power is going to be equal to the intensity of the sunlight times the area of the solar panel times the efficiency. Okay, this number here, the intensity times the area, is just the power of the sunlight that falls on the panel. Okay, we know that. The electric power produced would just be the intensity times the area. So at the distance of Earth, we have a particular solar panel that's producing 1.0 kilowatts of electricity. But that's equal to the intensity of the sunlight times the area times the efficiency. Now if we take that spacecraft and move it to the distance of Saturn, 9.5 times as far away from the sun, here's what's going to change. The area won't change. That stays the same. The efficiency of the solar panel stays the same. But the intensity changes. If they have the intensity at the Earth, it decreases when I get to the distance of Saturn. We know that. Okay, sunlight, as it spreads out, bigger and bigger radius, the power spreads out over a bigger and bigger surface. And so the intensity decreases. It's equal to the power of the source, i.e. the sun, divided by 4 pi r squared. So the intensity will decrease. So at the distance of Saturn, it's smaller. So as a consequence, I'm going to end up with a smaller power at the distance of Saturn. That's what we're asked to calculate. But here's the thing to note. The decrease in power is just proportional to the decrease in intensity. So if we can figure out by what factor the intensity decreases, that'll be the same as the factor by which the power decreases. So that's the question that we're looking for. What is the intensity of Saturn related to the intensity at the Earth? Okay, and if we know this factor, that's the same factor by which the electric power is going to change. So this is what we have to solve for. And let's do that. And to do that, we'll be guided by this equation right here. We know that the intensity at the ratio of the intensities of two objects at a distance r1 and r2 from a source are given by this. The intensity at distance 1 divided by the intensity at distance 2 is just equal to r2 squared divided by r1 squared. Okay? Well, let's take this equation and turn it into Earth and Saturn. The intensity at the Earth divided by the intensity at Saturn is equal to the distance from the Sun to Saturn squared divided by the distance from the Sun to the Earth squared. Okay? We're looking for the intensity at Saturn related to the intensity at the Earth. So I'll take this equation and turn it upside down, and we get this. The intensity at Saturn divided by the intensity at Earth is just equal to the distance from the Sun to the Earth squared divided by the distance from the Sun to Saturn squared. Or it's just equal to the distance from the Sun to the Earth divided by the distance from the Sun to Saturn, all squared. Now notice, this number, RE over RS, is basically given in the problem. Saturn is 9.5 times as far from the Sun as the Earth. So this just turns into 1 over 9.5 squared, which is equal to 1/90th. Okay? So the intensity at Saturn is 1/90th of the intensity at the Earth. And that makes sense because the intensity varies as 1 over r squared. So if you increase the distance by approximately 10, you're going to decrease the intensity by a factor of about 10 squared, or 100. So the power is just proportional to intensity. So the power at the distance of Saturn is just equal to the power at the distance of Earth times a factor of 1/90th. It'll only be 1/90th as much power. So that's equal to 1,000 watts times 1/90th, which is about 11 watts. And that makes sense because I have about 1/100th as much power, but that's because I have about 1/100th as much intensity. So my assessment is that my result seems reasonable in terms of what we know about energy and the intensity. But before we leave this, I want to point out a couple of things about the problem. It seems like you're not given very much information. You're told how much power comes out of the solar cell at Earth. You're asked how much power comes out of the solar cell at the distance of Saturn. Two numbers in the problem. We aren't given the area of the solar cell. We aren't given the efficiency of the solar cell. But what we know is that those numbers don't change, and so we don't need to know those numbers. We don't know the distance from the Sun to the Earth. We don't need to know the distance from the Sun to the Earth. We don't need to know the difference from the Sun, distance from the Sun to Saturn. We just have to know the ratio of those two distances. And ultimately, this is a problem that you can solve by using ratios. 9.5 times as far, 1/90th as much intensity, and so therefore 1/90th as much power.